Here we are at the second and final video for section 4.1. We only have 3 examples, but here we're going to go right away and attack those particular problems. We left off at example number 12, where y is equal to x squared times the square root of 25 minus x. And we are told to find the derivative at each critical point and determine those local extreme values. So we need to remember that the time or critical points are any place where the derivative equals 0 or where the derivative is undefined. And so what we get here is, I'm going to rewrite this in a user-friendly form. This will be x squared times the quantity 25 minus x raised to the 1/2. Now I see that this is a product, so I am going to have to use the product rule when I find the derivative. So I'm going to leave the first one alone, x squared, and take the derivative of the second. Well, to take the derivative of this is really a chain rule, but we should be able to do it pretty quickly. 1/2 times, leave the inside alone, change the exponent appropriately, and then take it times the derivative of the inside. Well, the derivative of the inside is -1. And so that's the first part of it. Then add, we will be adding the derivative of the first, which is 2x, and leaving the second thing entirely alone. Now just cleaning this up, we get, let's see, this becomes a negative x squared on the top and 2 times the square root of 25 minus x in the denominator, plus 2x times the square root of 25 minus x. Now, I do need to worry about where does this whole thing equal 0 and where it's undefined. Well, I know that it will be undefined whenever this is equal to 0, the 25 minus x. So that's not too difficult to do. Let's quickly calculate that. 25 minus x equals 0 is a problem, and so that means x equals 25. So that is one of the critical points. Now we need to find out when would this equal 0, and that's going to take a little bit more work. I'm just going to set that whole expression equal to 0. And solve from there. Okay, first thing I'm going to do is get rid of this, so I'm going to multiply through everything by 2 square root of 25 minus x. So that will leave negative x squared here, and then multiplying this whole thing by 2 square root of 25 minus x becomes 4x times 25 minus x equals, and 0 times that, of course, is equal to 0. So we get negative x squared plus 100x minus 4x squared equals 0. Clean this up a little bit more. And I see it's negative 5x squared plus 100x equals 0. I can pull out a negative 5x, and that leaves x minus 20 equals 0. So that means negative 5x would equal 0, which means x equals 0. Or x minus 20 would equal 0, which of course means x is equal to 20. And so here we have our 3 critical points. We have our 25 from way up above here, we have a 0, and we have a 20. Now, one of the best ways to deal with this is to put this into a chart. So we have critical point 0, critical point at 20, and critical point at 25. And what we need to do is we need to plug in these values for each one. So if I plug in, or if this is the x value, then the y value would be Okay, 0 squared is 0, and 0 times anything is 0. Plug in 20, and I get 400 times the square root of 5. After I plug that into the original equation, and then plugging 25 in, I get another 0. So there we get those particular values. And then we just need to determine, you know, are these, what sort of things are these? This would be a minimum, this would be a minimum, and this would then have to be a maximum, because a minimum occurs there or a maximum. Whether it's relative or absolute, you know, we really don't need to worry about it. We just want to indicate, since this is at the lower end, this would be a minimum, and this is at the upper end, so this would be a maximum. Number 13 is very similar, except it's piecewise. And so we just need to deal with it and realize that it only applies for certain amounts. Negative 1/4 x squared minus 1/2 x plus 15/4, and that is only as long as x is less than or equal to 1. Otherwise, it's x cubed minus 6x squared plus 8x whenever x is greater than 1. Well, we're still going to have to take the derivative both times, so I'm just going to split them up into two different parts and find the derivative of each one. So if I take the derivative of this top one, this becomes negative 1/2 x minus 1/2. Now the only place that this has a boundary, it has a boundary right at when x equals 1. Well, first thing we want to do is set that equal to 0, because it's defined everywhere, so there's no place that it's not defined. We set it equal to 0, so add 1/2 to both sides, then divide both sides by negative 1, so that x, or negative 1/2, so that x equals negative 1. So we've got a critical value, or a critical point, when x is equal to negative 1. It also may occur at 1, because this is an endpoint. So we need to check what would it be at 1, right at that point. And then taking the derivative here, this becomes 3x squared minus 12x plus 8. And unfortunately, this doesn't factor, but we do need to still set it equal to 0, and so we will have to use the quadratic formula. And so when we do that, we get x equals 12 plus or minus the square root of b squared is 144 minus 4ac, that would be 96, all over 2a, which is 6. And so this equals 12 plus or minus the square root of 48 all over 6. And if we look, this is only valid whenever x is greater than 1, so if we took the 12 minus the square root of 48 and divide by 6, that puts us less than 1. Or no, it doesn't. So we actually need to, that does not put us less than 1, does it? 12 minus almost 7 would be a little over 5, and 5 over 6, yeah, that is less than 1. So the minus we can't use. Instead, we're just going to use the plus. And shocking as it may seem, you are allowed in this instance, or in instances like this, to actually find a decimal equivalent. Let's take it out to 2 decimal places. So let's do 12 plus the square root of 48, and then divide by 6, and that gives us 3.15 as an approximation. So 3.15 would be a critical point as well. Now we can't forget the fact that we might have a critical point at 1 as well. Okay? And what we'll need to do a little bit of trickery there. But let's now plug in, what if we plug in negative 1 back into y, plug in negative 1 into y, and we will get a value of 4. Plug in 3.15 in for y, and we get a value approximately equal to negative 3.08. And so it would be very easy to see that this would be a maximum and this would be a minimum. Now let's look at what happens right at 1. Right at 1, we plug in y equals 1. Let's see, that would be what? Negative 1/4 minus 1/2 plus 15/4. So what does that equal? Negative 3/4, 12/4 is a 3. You get a 3 right at that point. Notice that that is not, that's not bigger than the max, and it's not smaller than the minimum. So really, it could have happened, but since it doesn't really fall into the category of being a maximum or a minimum, we know that the endpoint here serves or is not a local maximum, or is it a local minimum? And then finally, we have example number 14. And this is somewhat cheating, but we're going to do it just the same. I'm going to bring up the calculator. I apologize for not having it up already, so it will take a little bit of time to boot it up. But what we're going to do is we're going to graph this, and we're going to find the extreme values. We're going to look. We are going to cheat. We are going to graph it, and we're going to look at what happens when we actually do this. Now let's start out. Let's assume the default window, negative 10, 10, 1, and negative 10, 10, 1. And then go to y equals, clear out anything that we have. And to get into absolute value, I go to math. And I need to think, there it is. As soon as you hit the math button, which is right here, the second or the third one on the left, and if you hit or do the right arrow so that you're at numbers, ABS, that's the absolute value. So I want option number 1. I want the absolute value of x plus 4. So I'm going to do x plus 4. And you will need to close out your parentheses at that point. Mine, I've got a little bit advanced thing going on here, so I just get out of the absolute values. But then I need minus the absolute value of x minus 5. So I'm going to go back into math, go to the right one. Option number 1 is the absolute value, and that is x minus 5. So I'll do x minus 5, get out of that, and then graph it and see what I end up with. Now we can see fairly easily up here and down here. The question is, what value exactly is this? And that is the trick here that we really want to get to. So if you spend a little bit of time and just let's look at table. Let's see some of the values in the table. And then we will see pretty quickly that all of a sudden we have a whole bunch of 9s here. That's the maximum, at 10, 9, 11, 9. And you have to assume that it's going to go straight on forever and ever. And it does. So the maximum is going to be at 9. And let's see what we get when we look for the minimum. Going in the other direction, we get a whole bunch of negative 9s. And so negative 9 is this value down here. So it becomes pretty simple at this point. For number 14, we say there is a maximum of 9 on a certain interval, because it's not just at one point, it's several places. And that actually starts at the value of 5 and goes to infinity. And we can check that in our table. Let's go back to the positive 9. See there, it starts 5, starts the 9, and then it just goes 6, 9, 7, 9, 8, 9. So 5 until infinity, and it does include 5, will be the maximum. And then the minimum will have a value of -9, and that's on an interval as well. And that interval, if we go to the table, where does it start? It starts at -4, or actually it ends at -4, because what it is really doing is it's going from -infinity all the way up until -4, and -4 is the last time that it equals -9. Then we had that little stretch that goes from -9 to 9, here to here, and so that would be between -4 and +5. Now, you could try and estimate each of these marks, but it's a whole lot more accurate to go to the table and check it out this way. I do not need you, nor do I want you to do problems 15 or 16. So that, of course, would affect your homework. Your homework, you can throw out that whole last section as well. But now you are ready for all the rest of the problems, and I will see you in class.